for 30 years. He's got a card that lists a number of neat things that he can do for you in Duncan, Oklahoma. Custom specialty welding repair, commercial diving, machine work, mobile machine work, sandblasting, crane service. So he's one of these people that keeps the world running for us. And he's originally had a shop down in Marshall, Texas. He's recently moved up to Oklahoma. And he does a lot of measurements and repairs. And he was actually at the first Tesla symposium back in 1984. I've seen him around at many conferences since then, and we've kind of gotten to be friends, so that makes me a little prejudiced towards him. And I'm real happy to see him presenting here. So here's Forrest Pittman.
Here. I'm happy to donate my time in helping them, and I'm glad to be able to show you some interesting information I found that was handy for me in my business. And it's called power factor correction. Actually, that is a misnomer. That's the technical term for it. And what it does, you're basically tuning your power systems in your home, business, and community to optimal perfection. And it's done like you do a radio circuit. So what I use and industry uses is electrolytic capacitors, which are basically oil-filled. They make them all kinds of ways. The older style used to be with paper dielectrics, and the new ones now have film dielectrics with metallized coatings, so they can make them much smaller than were originally designed, and yet with better capacitance and higher dielectric constants. Some of your better dielectrics are mica and photocells, but the plastics and industry has some remarkable technology in being able to roll film the thickness that it is want and in metallizing. And I had the opportunity to tour a factory down in Port Lavaca, Texas, that they would roll some of this film on rolls 20 foot long and 6 foot in diameter. It was just absolutely amazing. Yet they had to handle everything very carefully because it would build up static charges is just unimaginable. It would arc several feet sometimes. So it was quite an experience. This particular cabinet here, I imagine everybody's dying to know what it is designed to demonstrate the principles of power factor correction. It allows you to measure. I don't have a cabinet like this for single phase. This is basically designed for industry and three-phase motors. So what I do, it allows me to measure the voltage on all three legs, the amperage on all three legs, and the amperage of the capacitance on all three legs, as well as having my, the frequency of the circuit. That was just an extra add-on. And then the switch here is to switch from 240 to 480. That allowed me a choice, because a lot of systems are designed for 240 or 480. And of course, it will work at 308 or 380 or 208. The switches are banks of capacitors, which I have to get closer so I can read them. The step one would be 3 10 microfarad switches, capacitors, and then each 10 microfarad is for each leg. Then I have over here another step two, another 3 10 microfarad capacitors, and then 3 20 microfarad, 3 40 microfarad, 3 60 microfarad, 6 60 microfarad, and 6 60 microfarad. And those are in parallel. And so what you do when you're testing a circuit, you just switch on the first one, and you just start watching your meters and the power factor correction meter until you start beginning to get a balance. And that way you're literally tuning the service of the motor in steps. And this allows you to get to basically 0 or 1 on power factor correction. and which is basically the ideal. I have tuned several people who had what you call a rotary transformer, and that's actually a single-phase motor running a three-phase motor, which becomes a motor generator. And what I did, I went in with my power factor correction meter, which is what this device is right here. It allows you to measure 2 legs at a time and get measure the voltage, and this current right over here measures the current. Now this meter is very special because it's got a computer built into it that allows you to know and measure kVAR. kVAR means 1,000 volt amps of resistance, CVAR. And that will tell you whether you have a leading or lagging phase according to the percentage of the error. Most industry likes to correct to around 95. I like to go clear to 0 so you have a truly balanced system. They want to have a little lagging phase in there, so it costs you a little more. So I try to work for my customer, not for the power company. This box here is designed for single-phase power to invert to three-phase and give you starting capabilities and run a three-phase motor on single-phase power. And it's basically set up to run at a 1-horsepower motor to about a 2-horsepower motor. And it'll start and reverse a motor either direction. And mainly on three-phase, to reverse a three-phase motor, you just switch 2 of the legs and it'll reverse. And it's pretty simple. On reading my meter, it has a number of scales. So what I do, I read the scales and then mark it accordingly for normal and peak. And I chart it and write it all down because on this first normal scale, it's a floating scale. The meter's constantly changing. It has a switch on it that allows you to average your power as the machine fluctuates while in operation. And I a lot of times take that to get just a rough average on the first normal scale. Then I go ahead and mark my peak amps, peak watts, and peak volts. This helps me, and they'll all be just slightly different. It's just the way the meter's set up. And I don't know quite why it works that way, it just does. Now there's another way you can work if you do not have a power factor correction meter, and I'm going to draw a rough picture on the board, is you can use an amp probe like this. You just slip this around your cable, just like you did with this other one, and that'll allow you to test the circuitry of all 3 legs. Say you have an induction motor, shaft out, you got a little power box here, and say it's single phase, you just got 2 wires, actually 3 wires go in, one will be for ground, the other 2 will be for a leg. Now what I do with mine, I take the power factor correction box and put it here, and then one set of wires will hook here, the other set will hook to right here. Now, when you measure with an amp probe like this, you first make your measurements right here. You really only need to measure one leg on a single phase because the other leg is going to read basically the same. So, but when you start working it, this leg, when you measure right here and right here, all 3 are going to be totally different. So if you have an amp probe like this, and what you need is small electrolytic capacitors, and you can buy yourself a little box. And this in here is a 10 microfarad capacitor. At 120 volts, this is will correct you about 1/3 of an amp. 120 volts will average about 25 microfarad for 1 amp. of correction. At 240 volts, this 10 microfarad capacitor will correct about 1 amp. So as the voltage climbs, you need less capacitance. So what I do, like right here, for instance, I take my meter, I gradually add, say I take 10 microfarad capacitors. Then I put one in the circuit and make me a measurement here. How much amperage is it drawing? And I make a measurement here. I don't really need to measure here because I know about what it's going to be. My ideal is have the least amperage on this side of the circuit. So if the motor normally draws, say, 10 amps, and I add 10 microfarad capacitance, this will drop maybe down to about 9 amps, maybe. Then as you add another capacitance, it'll drop a little bit more, maybe about 8 amps. I'm just figuratively speaking now and keeping the figures round so it's easy to remember. I like a digital meter because it gives you right down to the decimal point. And then as you add another one, let's say we just go, okay, then it might drop down to 7. Now figuratively speaking, say we add now say we add a fourth one. We add a fourth one, all of a sudden it might go back up to 8. Now we've reached the peak. We know we need to stay with 30 microfarad. And that, because when it starts going back up, you can keep adding them, but your current will start going up here. It'll go back up almost in the same step ratio as before you started. But you will start drawing a lot more current because that acts as a resistive load as well. But the ideal is get the least current on the input power side of the motor. Now the current here will still be 10 amps. It'll remain the same. And in fact, it might go up just a little bit because of the extra capacitance. That's because of the reflection of the inductor, the field in the motor, to the capacitance that you are adding. What is happening, as the phase changes back and forth, your reactance and capacitance tune the circuit, and it makes it much more efficient. And when you reach a peak, there becomes a balance. Now, if you go over the peak, it is basically said you are overcorrecting your circuit. And you don't want to do that because it'll actually make you draw more power from the meter. But if you correct it into a balance, like 0 or 1, then you're close enough. So you want to stop right here. Now, on a 3-phase motor, it's the same thing.
Where's the power meter in that diagram?
The power meter?
Yeah.
I'm just showing you with current right at the moment. The power meter can be connected, your little volt ohm meter, and this little, I think it's about $25 Radio Shack meter or less.
The one on the house that built this.
Oh, you're on your side of the power meter. You don't want to touch anything on their side of the power meter. Because the power on your side of the power meter is what you're paying for. Everything on their side of the power meter is their responsibility.
So
now,
if we put it on our side of the power meter, the current is low, but it's still high on their side.
no, it isn't.
No, okay.
It will start coming down.
Okay.
As you correct each individual motor, one at a time, the power will gradually start coming down. And that's one of the reasons I got into it, because I had 3 air compressors. I have a 2 horsepower, a 5 horsepower, and a 25 horsepower. And when I would do sandblasting, and that was when my power bill really went up because I was drawing a lot of horsepower. So I found out when I bought my power factor correction boxes from Steelman Industries for the size of the motor, they were really undersized, almost half of what they should have been. They don't give you all the correction you really need. So I began to figure that out. I said, I got to find out. So I bought the power meter. It was quite an investment. It took some time to earn the money to pay for it. It was right at $1,200 for me. But after I bought it and I started making measurements, I started figuring out where I was using more power than I needed. So I went to Steelman and I started buying capacitors from them. And fortunately, the boxes they sold me, there was extra room inside, and I was able to parallel wire the capacitance to the original circuit, and it worked fine. Didn't overload or anything. But on your three-phase, it's basically the same scenario. We'll put this last one as ground. Okay, these three go over here, and in your power box here, same thing again. You hook one here, and one here. The procedure for measuring and correcting will be exactly the same with the amp meter. So what has happened on a three-phase motor, whether it's delta or YYY or something, on delta it's basically like this, which most people have. If you're in a real industrial area, you'll have true three-phase, which will be okay. Now, what I did, we basically are putting capacitance on each leg. Like that. And that's what this box does here. Now, on a YY circuit, it's the same thing, but instead of having a middle, you got each leg like this. Now, the correction is exactly the same, or virtually. But you can go from ground to the capacitance here. Let's see. Wait a minute. Okay. I'm not getting my ducks in a row right. To there. You can make it neat and make it all the same side all the way around, but it doesn't matter the order you have it as long as it's in the correct wiring system. A lot of times your wires won't go right where you want them to go to make it look neat. These are just basically two examples. On 240, it's the same thing as single phase, like 120 volts. See, 120 volts will be a little different than this because actually you're using one ground. Let me show you that circuit so you'll have a grasp of it. Yeah. In a sense, you have a neutral and a ground. So this is 120. Your power box will hook up exactly the same as on the 240. It's really quite simple, but it takes a while for your mind to go there. It did me. Okay. On this box, as we described before, these are three-phase legs, and this box is designed to go from a 1 horsepower motor clear up to a 100 horsepower motor, and I can correct it for its losses up to that size. And these each of these cables. The reason I had them made so long, sometimes the motor from the machine is considerable distance from where you had to park this thing. And usually you have a handful of engineers scrutinizing everything and do your best to try to answer their questions. I hope I haven't gone too fast, but I'm going to start early and allow anybody to ask me questions that if I can possibly answer them. John, would you mind with a microphone?
Okay, Forrest. I tell you what, for this portion of it, would it be okay if they came down and actually, if we started a line, say, right here? How's that sound?
That sounds fine to me.
Would that be okay?
I have no problem.
Okay, let's start a line right here.
I want to
And that way, if they want to point to something on the equipment, or you can give them direct instruction. Our first contestant, request lines are open. Next victim, please. Next caller, please.
Yes, sir.
For the average house, is there some rule of thumb that you could say, where the fuse box is and the meter, on our side of the meter, is there some average amount that would probably help each household on the average, like 10 or 20 microfarads?
Yes and no. The power companies are beginning to outsmart us. And here's what's occurring. The older meters were based on wattage. The newer meters are based on amperage and kVARs. And what is occurring, if you still got one of the older meters, yes, you can put you a 50 or 60 microfarad capacitor across your 240 power, and that will save you probably 10 or 20% just on your electricity. But if you got a new meter, it's actually going to make the bill get higher because it's measuring the reactive resistance and higher load of the capacitor. Instead of correcting the kVARs, it's
okay,
changing it.
You're saying that the old ones really measured power, but the new ones measure the volt amps.
Volt amps, correct.
The KVA.
KVA,
which
and therefore you lose if you try to correct at the main. So right now, instead of advising people to correct at the main, I'm backing off of that because of the new meters. I would suggest correcting at your refrigerator, freezer, little air compressor, and hot water heaters. Now, what's neat with electric hot water heaters, you can put capacitors in series and parallel to limit the heating draw of your hot water heaters, and it just heats up slower.
In our home, we have a big commercial refrigerator, freezer refrigerator combination, and it's the biggest power draw in our house for sure. And when it kicks in, you hear it like a freight train,
Right.
Now, is there some rule of thumb you could use as to what capacitor to put across a big
Well, we first need to figure out what the horsepower of the compressor is. What I would suggest to do, they have a start and switch. We need to measure the amperage of the motor. So, 1 horsepower motor roughly draws 746 watts, which is 1 horsepower in wattage. Most electricians just round it off to 750 watts. But what the starting draw will be probably 1,000 watts or more. What needs to be done is you need to measure the amperage on one leg off that compressor to get an amperage reading, and then multiply that times the voltage. Power law is kind of important to know. I'll show you that. Power law is basically, I like to make it like a pie. It's easy to remember. You just put it in a circle. And same way with Ohm's law.
Yeah, I'm trying to ask questions that would apply to many people, not just my specific thing. And so I hope that if the people bear with me here, it'll help a lot more people than just me.
By the way, just
Okay.
a side, oh, go ahead.
This up here is Ohm's law, and this right down here is power law. So in Ohm's law, you can find E when you multiply I times R, or if you don't know I, you can divide R into E and you'll have I, or I into E and have R. In power, or watts, sometimes motor placards will have the wattage on it, but you don't know the current. Well, you can divide the voltage into the wattage and you'll have your current. Or vice versa. If you don't know the wattage of it, you can take your volt amp meter like this one right here again, measure your amperage. You know what the voltage is already because you know what's coming in. You multiply your amperage times your voltage and you'll have your wattage. It's very, very simple, but sometimes it takes a while to acclimatize to this system of thinking.
So if our big machine had a 1 horsepower motor on it, is there a typical capacitor that would?
On my big air compressor, I use 60 microfarad capacitors, and I use 3 on each leg, which is 180 microfarad per leg. And I found that was still not enough. I went up to 240 microfarad per leg, and then I began to reach 0. And the motors actually gain a little bit in torque, not necessarily more in horsepower, but in torque.
Okay, thank you.
You're very welcome.
Okay, now in my home we have refrigeration air conditioning. When it gets up around 100 degrees Fahrenheit, it doesn't work too well.
Mm-hmm.
Now, could your power correction make that work a lot better and cool the house down better?
You're dealing with the thermodynamics there. The compressor is probably running correctly.
Mm-hmm.
You're probably running into a heat loss problem, and that's probably your condenser. Your condenser needs to have a way to cool itself a little better.
Yeah, we think it might be filters and possibly need some coolant or something, but
Well, unless your refrigerant is low. Now, if your refrigerant is low, you're overworking the compressor, and it's not having enough volume of Freon to carry away the heat.
yeah, that might be
The
it, yeah.
heat is compressed, and then the liquid then goes to the evaporator where it is cooled, and then that is then pushed back through into the evaporator side of the core through an orifice, which allows the gas to expand several times its volume, and in expanding it becomes cold. And then the cycle is repeated. You must, to get the heat out of that expanded gas, you got to compress it again.
But when it gets a little cooler, like in the evening, like when it's around 80 degrees, it works fine, you know.
What might help is to check and see if the drain is not rusted out on your air conditioner, because a lot of them are made to collect a certain amount of water in there and splash it on the condenser to help keep it cool. Sometimes you can actually squirt the water hose on it and it will help cool it.
Oh, okay.
That's
It
a very
won't
common problem.
It won't short circuit when you put the hose on?
No, they're designed to splash in water a little bit.
Okay.
They won't overfill, but a lot of them get lots of dirt in them over a period of time because they're never cleaned.
Right.
And it's good to pull the air conditioner out and take it outside and wash it out with a water hose and make sure all the little drains and orifices where the water catches are cleaned.
Okay, well, thank you.
You're welcome.
On a 120 volt motor, a single phase motor in the house for a fridge or something, where do you put the capacitor from?
Okay, if it's in a freezer, you're going to have to pull off the back of your freezer. You need to find out where the starting switch is that runs off the thermostat for the freezer. You can put this capacitance between that starting switch and the motor. And you could actually just wire it right directly into the motor, the capacitor bank. But you don't want to leave it where it's engaged all the time. In other words, the starting switch will start the motor and the capacitor bank together. This allows them to, thank you.
But you don't put the capacitor in series, right? You put it from one leg to
Yeah, you
neutral or
parallel
ground.
connect the capacitor across both legs, whether it's 120 volts or 240 volts.
But
See?
do you mean to put it from the leg to ground?
Sure,
Or
yeah. Okay, like the motor right here. Say this is your air compressor, okay? This is a capacitor bank. What I'm doing is I'm putting it, this is for three-phase. We better do it for single-phase. This is 120 volts. Your capacitor, this little device right here, you take two wires off of it and connect it to each leg. One leg is a neutral, the other leg is a hot leg. Be sure you unplug it before you connect it. It might light up your life, you know.
Okay.
But this will be your little box here is your sensor for the freezer. I don't know if I spelled it right, but anyway, do you understand?
Okay, yeah. Is it the same thing for a 240 volt motor?
Yes,
Like my
exactly the
pool
same
pump?
thing, but less. See, remember, this takes more capacitance for 120 volts than it will for 240. On 240, 1 amp is about 25 microfarad. 1 amp let's see, this is 120 volts, and 240 volts. 1 amp is about 10 microfarad. This is a rough rule of thumb. It's not exactly, but it's close enough because most of the capacitors come in 10, 18, 20, 25 microfarad. And you can tune it. But again, using the amp probe will help you determine how much you want. Sometimes you might be able to borrow some from somebody till you get it tuned. What I did, I go buy several electrolytic capacitors, clear down to 2.5 microfarad, and you can add them. And when you start seeing you get a balance, you know where it is. Then you can take your circuit loose. You just look at the labels on every one you added, and then you put in a big capacitor of that capacity. You don't need the little ones anymore. They were your tuning device.
Thank you very much.
You're welcome.
What would be the difference if you just did a mathematical calculation on it?
Not any difference. The problem is most people don't know how to do it.
But
So-
would it be easier than doing a trial and error method?
Sure, but not everybody's capable of that. In fact, the majority of people are not capable of that. So what I try to do is I try to bring it down to a level of understanding to where people can do it by trial and error and learn from that.
How can you prove you got a power factor of 1?
I find out because I use my meter. But if you're doing it for yourself, you look for you're pretty close to 1 when you've added the capacitance and you're measuring the amperage, like over here. When you measure the amperage on your incoming power to your motor, and as the amperage comes down, and then when you see the breakover point where the amperage starts going up, you know you've added too much capacitance. You want that amperage at the lowest input possible, and you know it's at a reasonable balance then.
Most people would only care about having that low amperage right at the meter. And
Right, but-
sometimes what you would do there might affect the opposite direction as your meter.
Well, when you correct it at the meter, it affects everything in the house.
That's right. If you got a high resistive load and you overcapacitate it, you can go the opposite direction.
That's correct.
So
But
why
every
not-
little motor, light bulb, fluorescent fixture, everything in your house, when you correct it right at the meter, on your side of the meter, it will bring the power down. But again, because of the new meters, you need to find out whether you got a new meter or an old meter. If you got an old meter, you can correct it right at your power box, but it will correct everything in your house, including the air conditioner, the refrigerator, and the freezer. But remember, that capacitor remains on all the time. When you correct it at the motor, behind the switch, that circuit will be there all the time, but it's only on when that device is running. That way you have the best efficient correctness. Of course, to keep the light bill low, you keep the switch off until you need it. That's how I found out the best way. I used to leave my compressors on a lot, and always keep my air filled, and I kept wondering, how can I get my power bill in? So I started trying different things, and I tried the power factor correction, but one of the best ways to keep your power bill down is to keep all the switches turned off. Only turn on what you need. That means lights, other than refrigerators and freezers where you're keeping perishable goods, should you leave on.
Average house, if it had fluorescent lights, it probably wouldn't need any capacitance, would it?
Some of the newer fluorescent fixtures are power factor corrected. Most of the old ones are not.
Thank you.
You're very welcome.
Well, I'm here to represent the power company.
Oh, okay.
I used to be an electrical test engineer at a 2,000 megawatt power plant.
That's a big capacitor.
Yeah, that's seventh largest in the United States of fossil. It's located in the Four Corners area, but we feed Phoenix and out toward the Lake Mead switch yard through a 500,000 volt power line. And I'll tell you what the problem is. Your VARs are constantly changing the load in your load, and that applies to the generators. Example, we had two big units, 750 megawatts each, and one fed to the Lake Mead switch yard by Las Vegas, the other one went to Phoenix. Mm-hmm. And they measured, instead of kilovars, they measured megavars, which is volt amperes reactive. And what it amounts to is the reason they change, you have to look at the load. The load is, for power companies, is mostly inductive because you're looking at transformers. All the pole transformers and distribution transformers are all inductive. All the motors are all inductive. Pure resistances are not really common, like light bulbs and things like that. So in your house, when your air compressor turns on and your air conditioner turns off, your load changes.
Exactly.
And so there's not a one-size-fits-all for everything.
Nope.
We had to, there's a gigantic capacitor bank for each of the big units up there, and when the megavars began to come up on the megavar meter, we would switch in more capacitance, and it would drop back down. And
I have a suggestion, and I've made this to a couple of power people, and they basically ignored me. But this involves the pole pigs that feed the distribution to the houses. Mm-hmm. If they would power factor correct the primary on the pole pig to resonance, the reason I say you can do it on that because the wire is long and lots of the turns, depending on whether it's 7200 or 14.4 or 36 or 33.3. Mm-hmm. If you power factor correct it there to resonance, that transformer load basically drops off the line because it's basically if you do it to where it's in balance, true balance. Now, the only time that load will come on the line and affect it very much at all is when the secondary is having power drawn on it, like from houses.
Yeah.
Now, the power company could correct the secondary on that pole pig to say 30% or 40%. That pole pig then would actually become over unity and pump power back into the line, even under load. They don't do that.
Where does it come from, this excess power?
Reactive energy, because it downloads back to the power line if there's a load in each half the cycle. It's kind of a unique feature, but it works. I tried it just for not a demonstration, but for my own benefit. I've got 5 pole pigs. I got 2 25 kW 7200. I was going to use for 3-phase, but it's the wrong voltage. So I played with one of them, and I made me my own capacitor. I didn't know where to find one, so I've got a big, huge variable capacitor. So I hooked it up and tuned that first leg to see what would happen.
Well, you can go for minimum, but you never can go for zero.
No.
And the correction, the power factor correction that the power company does is at the switch yards and at the power plants.
Right.
They can't afford to go to every single power pig on every block, pole pig on every block
No.
and tune them.
This is
So-
a long-term correction. They could do it, do them just like you do your house, one at a time.
Yeah.
What they do, when they buy them, once they find out what the resonance of a particular size pole pig is, before they install new ones, because they have to replace them occasionally, they just replace that because the capacitor can be made fairly cheaply, and it's not very big. You're dealing with probably 1 or 2 microfarads, if that.
Well, it's still a function of the load
Yes.
that they're seeing, because residences have, part of their load is inductive, like compressors for air conditioners and so forth, and part of it's resistive.
Resistive.
And so it's
Well,
constantly
inductive loads and resistive loads are always a lagging phase. Yeah, it's always
Yeah.
current related.
Yeah.
Inductive and resistive loads are to amperage as capacitance is to voltage. So the ideal is to find a happy balance between the two, which you can't always achieve exactly like you do in tuning a radio, but some is better than none.
Yeah, well, that was a big deal there, and they watched those megabars real carefully, and they never stopped changing. The load never stops changing.
That's correct.
Are you ready?
I'm ready.
All right. On a motor, you already have a capacitor and a starting winding, correct?
Correct.
Okay. Now then, after the motor started, you're into another winding.
Right.
This is the winding we're going to correct.
Correct.
Okay. It's the reason we're correcting it is just like the starting winding. It's going from back and forth, alternating current. Every time it goes from one to the other, it would be like starting the motor again. So we're putting a capacitor in there to give it that extra boost. Is that correct?
It actually helps both the starting coil and the main running coil.
Okay. Now then, rather than I have one of these boxes that's probably high $1. If I had a pocket full of capacitors, I just keep plugging them in until I get the right reading.
I fudged like that too. What I had
Is that
done,
right?
I did with my refrigerator, and it sounds kind of simple, but the refrigerator motor is about 1 horsepower on 120 volts. It would require about 90 to 100 microfarad. But I had some 60 microfarad capacitors, and I had some old appliances that had burned out, but I still had the extension cords. So I fudged, and I got me some little spade connections, and I put it on the end of the extension cord and plugged it into the wall where the refrigerator works. Since it works most of the time, it actually made my power bill come down, just plugging it into it, and it was running all the time.
Well, another little thing, after you got a charge on that little booger right there, it'll bite the dickens out of you, won't it?
See that little blue resistor soldered between those terminals?
Yeah.
Okay, the reason for that's about 45,000 ohms of resistance. The idea for the resistor is
To bleed it off.
to bleed it off within about 1 or 2 minutes. This way, you won't light up your life and give you a charge you don't want.
All right, but now this box, you use it to test your refrigerator. You put the capacitor in, then you take this box over here and you try it. Or does this box have to stay with that one motor?
Well, if you do the little simple way, you can actually get little brackets. You don't even have to put this in a box. When you're underneath the refrigerator and you pull off the back cover, and you go in and you figure out how much capacitance you want to put in there, you can wire this capacitor, screw that bracket to one of the brackets in the bottom of the refrigerator and run the 2 little wires over there to you can put spade connectors into spade connectors that hook that system together and wire it, and it'll sit there and work for as long as the refrigerator operates.
What I'm trying to find out is I'll hire you to bring your box out and find out all this information for me, put the capacitors in, and take your box and go home. Is that what those boxes are for?
Well, this
That's
box
what I'm
here
trying
is
to find out.
basically for industry and factories. What I usually do is I take my power meter right here, and I take my little chart to your house, and I make my measurements and figure out what size capacitor I need at the right kVAR, and I'll just bring a box of wire. That's why this box is full of wire. It doesn't take very much wire to do anything. I just use little spools of wire like that. Now for big systems, I require much bigger wire. But for a refrigerator or a house, you're not drawing very much amperage. You might jump.
This is what you said, $1,200 meter? I can't go out and buy a $1,200 meter. I'm going to have to hire you to do it.
That's why I was trying to show you how you can use an amp probe. These are only about 50 or 60 bucks.
All right, with this, you're just taking a reading with this equipment. I have to figure out which one of those capacitors to put in there before I make the reading.
Exactly.
So I'm going to have a whole bunch of capacitors, unless I hire you to come out and figure out which capacitor I need.
That would be your choice. Some people like to be innovative, you know, and I had to do that myself. I had to hire somebody to do some of this for me. But the problem is there's not very many people who know how to do this.
Well, I know how to get in trouble, and that's what I usually do.
Most electricians don't even know what you're talking about when you have power factor correction. And usually when they order a box like this, they order it by the size of the motor and the wattage it draws. And usually they're way under-corrected. But when I correct and go and make my measurements, I correct it right to exactly what the motor needs. So you're better in balance and got a better buy.
I thank you.
You're welcome.
Hi, my name's Randy Wood. I've got a few questions. First question is, when you're selecting capacitors to use, what sort of voltage rating should you get for your capacitors? For example, if you're putting it on a 120-volt line, what kind of
well, capacitors like these right here usually come in, I think this is 370 volts AC. And that's about as small as you're going to get them. So this would work for any 120 volt circuit. It would even work for 240 volts. You want to be sure always the capacitor voltage of operation exceeds at least 50% of the operating voltage of the appliance or a piece of equipment you're correcting.
Okay.
That way you have a safety margin. If you can double it, that's even better. That way a lightning strike and a real spike might not fry it inside and short it.
Okay, and maybe the capacitors will last longer that way as well.
Yes, they will.
Okay. I would like to make a comment on the whole house correction versus at the individual equipment items.
Sure.
And the problem with trying to do a whole house correction, as I see, is that because all these different loads in your house aren't on all of the time, you either have to make an estimate of what your average load is and try to correct to that, but if you have things turned off,
it won't be a load at all.
Well, as your load varies, you're either under-corrected or over-corrected.
Well, I suffered that very problem.
In conditions, if you're corrected the wrong way, then you're drawing more power than you want to. Whereas if you're doing it at each of the individual items after the power switch for the device, then it only comes on when the device is operated. So you're not affecting the rest of the house with your.
That is absolutely correct.
Okay.
I found that problem. See, I've got a 160-acre farm and a farmhouse and a water well, refrigerator, and I don't have it's a refrigerator and freezer. When I first inherited the farm, they hadn't changed the meter. So I put, I think it was about 25 microfarad up in the attic. I mounted the power box on the wall and wired it in. And I brought my bill down to about $25 a month. And then all of a sudden, I started getting $50 a month power bills. And I was running a refrigerator and normal in the water well. And I went and looked at the meter and it was turning. And so I started going around turning off everything. And it's still turning. What's wrong? I had to think about that a while. I completely forgot about my power factor correction on the box. I went home, and I still got another bill. So I had turned off everything, including unplugging the refrigerator. And it was still using power. And the next month, I think it went down to about $35 or $40. See, I don't live out on my farm. I just stay out there sometimes on weekends to help mow and fix fence. I got another farmer leasing my property. But anyway, I still was flabbergasted. I still hadn't thought about those capacitors. And then it occurred to me, at least it was almost 2 months before I figured it out. So, but my house at home in town, they hadn't changed the meter. So anyway, after I figured it out, I put a switch on the side of the box so I could switch them out to repair them if need be. The next month, the bill came down to about $20. That's where it happened. Well, I'd say, maybe they changed the meter at the house. Well, my power bill the next month was $225 for a refrigerator and another separate freezer and running air conditioner. I was flabbergasted because I turned off the capacitance there, thinking they had changed the meter there too. Well, that's PSO rather than REA. The REA, they're updating everywhere, I guess. I don't know. But so here last month, I turned the capacitors back on, and my power bill came right back down again. So it's a matter of trying to figure out where your losses are. And even to somebody who knows, it still confuses you. So I don't pretend to know it all, but I do my best to try to help everybody that asks.
Okay, greatly appreciated. One more question,
Sure.
if I might, and that is, if you have a device, some sort of equipment that has a variable power setting and so forth, which power setting or mode of operation should you try and make your correction for?
I set mine to the optimum. In other words, when a compressor is at no load, it draws its least power. When it goes to full load, in other words, the air tank is getting fuller and fuller and fuller until it reaches its 150 pounds or 175 pounds. The motor then is under its maximum load. It is also drawing its maximum power. So the ideal is to set it at its maximum for the motor under full load.
Okay.
Then when the load goes down, it also goes down on the capacitors. But remember, the capacitors' reactance still keeps the field at full strength. The current goes down because also the load has gone down on the motor.
All right, thank you.
The tuned circuit doesn't change.
If I may get a second chance here.
Anytime.
Our last power bill in Downey, California was $415.
That's like paying the bank.
Now, how much would you charge to fly out? No, in your own community, how much would you charge to go to your neighboring homes and actually psych out their problem and charge them for your time plus any capacitors that you had?
I normally charge $65 for a service call for making the measurements and trying to figure out and find out what the problems are. It takes more than an hour of time, and then you got your time of driving there. But in a small community like in my home, you're looking at about 35,000 people, and it's not that far to go.
Okay. How much does a typical 10 microfarad capacitor cost?
They vary in price. Some like this are about $10 or $15.
Okay, that's reasonable. And so, do you perform this service in your hometown?
Mm-hmm.
Okay.
But most people don't have a clue what I'm doing.
You're right. You have all the
highfalutin. I rarely ever get calls unless somebody is recommended because they were happy. That's all I want.
Of all the highly technical presentations we've had, yours is probably the one that hits home the most, and really means the most to everyone here.
Well, this is something everyone can do. It's just a matter of understanding some of the fundamentals, and I like that KISS principle. You know what I mean.
Now, if you have the capacitor correctly placed on your refrigerator, when the refrigerator shuts off, that capacitor is removed It's not on the rest of the house?
Correct.
Yeah.
That's what I recommend. Although I'm still fudging, and some of mine are still plugged into the wall behind the refrigerator.
Yeah.
The refrigerator cuts off, but the capacitor still stays on.
That's
Now,
right.
If they change the meter on me, I'm going to have to pull the refrigerator out and go to the trouble to take the back off and go in there and wire it in like it's supposed to be.
Okay, thank you very much.
You're welcome.
Well, Forrest, I'm impressed. Ladies and gentlemen, Forrest Pittman. Oh, by the way, do you charge gas to drive out to check their house?
Run that by again.
Do you charge fuel or travel
Not in the
expenses
city-
to go
not in
visit
the
their house?
city. Now, if I gotta drive out in the
so if I live
country-
in Tahiti, you're going to come out for free?
Ooh.
I just thought I'd mention that. Okay, if we could have a little bit of help helping Forrest reload up. Forrest is going to pull his truck around here, and I'm going to need actually, to reload this back up, we're going to need at least 4 to 6 good strong backs. We can stop the recording now.